The most frightening answer to the Fermi paradox may be this. Civilizations do rise in the universe, but almost all of them disappear before they can be seen. Somewhere between life beginning on a planet and intelligence reaching the stars, there may be a hidden barrier, a great filter, and if it is real, then the silence of the Milky Way may not be a mystery at all. It may be a warning. In this video, the story follows that possibility through cosmic history, planetary chance, biological rarity, and the fragile future of intelligence itself. If this kind of science storytelling speaks to this audience, please like, subscribe, and share. Every bit of support means a great deal, and thank you for being part of this channel. It would also be wonderful to hear what time is it right now, and where in the world is this being watched from, and now. Let us begin the journey. Enrico Fermi stands near the foundations of modern physics like a figure cut into stone. His name attaches itself to the hidden rules that govern matter at its most intimate scales, to statistics that describe how particles arrange themselves, to reactors, to laboratories, to an entire era of 20th century science that learns to look beneath the surface of the visible world and find a deeper order there. In the history of physics, he is remembered for work of enormous consequence, work that helps explain why stars shine, why atoms behave as they do, why the modern picture of nature acquires such sharpness. And yet one of the ideas most strongly tied to his name emerges not from a grand theory or a polished calculation, but from a small turn of thought. It begins with a question so plain that it seems harmless at first. It asks, in essence, why the universe appears so empty of company. That question survives because the setting around it is real, measured, and vast beyond any instinctive sense of scale. The Milky Way is not a sparse scattering of stars, but a full and structured galaxy, a spinning city of light containing something on the order of hundreds of billions of suns. Modern astronomy refines the number, shifts it, debates the exact count, but the conclusion does not change. The galaxy is crowded. It stretches across about 100,000 light years, with spiral arms braided around a bright central bulge, dark lanes of dust veining its disk, and countless stellar systems moving through it with slow, patient inevitability. Around many of those stars are planets. In the last few decades, observatories on Earth and in space begin to uncover those planets in large numbers. Tiny dips in starlight, faint stellar wobbles, rare moments of direct imaging, and the careful work of missions such as Kepler reveal that planets are not an exception. They seem almost to be a natural byproduct of star formation. Once that realization settles in, the old picture of a lonely solar system begins to dissolve. The arithmetic of possibility then becomes difficult to ignore. If even a modest fraction of the galaxy's stars possess rocky worlds, and if even a modest fraction of those worlds carry liquid water at some stage in their history, and if chemistry on at least some of them finds a path into biology, then the Milky Way should not be a silent museum of sterile suns. It should be a place where life has had room to experiment. Some of those planets must surely be older than Earth by immense spans of time. Their oceans would have formed earlier. Their continents would have shifted through more ages. Their biospheres, if biospheres exist there, would have had a longer run at complexity. The galaxy itself is more than 10 billion years old. That is enough time for repeated attempts at life, repeated failures, repeated recoveries, repeated climbs toward intelligence, perhaps again and again, across distances so large that human imagination flattens under the burden of them. And still the sky offers no clear sign. The silence is not absolute in the simple sense. Space is full of noise. Pulsars flash like clocks. Quasars pour out power from the hearts of distant galaxies. Supernova remnants glow in expanding shells. Clouds of hydrogen murmur at radio wavelengths. black holes feed, magnetized stars crackle, planets eclipse their suns. The universe is busy, violent, and full of signals. But none of that known activity answers the deeper expectation that grows naturally from the scale of the setting. Nothing in the sky clearly announces the work of another technological species. No engineered beacon sweeps across the radio bands with a pattern beyond natural explanation. No vast structures eclipse stars in ways that force a single extraordinary conclusion. The heavens are active, but their activity remains, so far, compatible with blind physics and unplanned chemistry. This is where the unease begins, not in fantasy, but in the gap between what the numbers seem to allow and what observation actually reveals. The question gains force because Earth itself exists as a proof of concept. Somewhere in the universe, matter does wake into metabolism, memory, and thought, because it has already happened here. On one small world circling an ordinary star, chemistry crosses some hidden threshold long ago and begins the long work of becoming life. Much later, after uncounted extinctions, mutations, collisions, and climates, a species appears that can build radio telescopes, launch probes, and wonder whether it is alone. That fact changes everything. Once one civilization exists, the idea of many ceases to be absurd. The universe has already demonstrated that minds can emerge from matter. The mystery is no longer whether such a thing is possible. The mystery is why it does not seem to have happened often enough to leave a visible trace. This is the heart of the paradox associated with Fermi. It is not a contradiction in the mathematical sense. It is a pressure between abundance and absence. There are too many stars, too many planets, too much time, and too many opportunities for the galaxy to look this quiet. If intelligent life is common, then the Milky Way should, by many simple lines of reasoning, already bear marks of its presence. Civilizations with even a slight head start on humanity would have time to explore, to transmit, to build, to alter their environments, perhaps even to seed machines across interstellar space. The galaxy is old enough that a technological species does not need to master impossible physics to become noticeable. It only needs persistence, patience, and timescales that astronomy grants in abundance. 1,000,000 years in human history is almost incomprehensible. In galactic history it is a brief episode. 10 million years is still brief. Even 100 million years is a narrow slice of cosmic time. If any species learns to travel slowly between nearby stars, or even merely to send durable machines that copy themselves using local material, then a galaxy can in principle be crossed, sampled, or transformed long before its stars grow old. Yet no such transformation is obvious. That missing evidence does not prove emptiness, but it darkens the scene. It suggests that something in the chain from planet to civilization fails more often than intuition expects. Perhaps life rarely begins. Perhaps complex cells are a freak event. Perhaps intelligence is not an inevitable flowering, but a narrow and unstable branch. Perhaps civilizations do arise but vanish quickly. Perhaps they hide. Perhaps they spread in forms too subtle to notice. Perhaps the instruments on Earth are still primitive against the scale of the challenge. Every answer seems possible for a moment. Each answer also opens a more troubling question. If life is common but intelligence rare, why is intelligence rare? If intelligence is common but brief, what ends it? If advanced societies endure, why do their works leave no unmistakable stain on the galaxy? If they are present but invisible, what kind of presence escapes a species already scanning the sky with sensitive radio arrays, optical surveys, infrared telescopes, planetary probes, and patient algorithms? So the mystery does not begin with stories about visitors, crashes, or secret archives. It begins with astronomy itself. It begins when measured reality becomes strange under its own weight. A galaxy rich in stars ought to feel full of possibility. Yet the deeper its population is understood, the more severe the quiet becomes. Every new catalogue of exoplanets sharpens the question rather than softening it. Every improvement in telescope sensitivity, every map of the Milky Way's structure, every estimate of how many worlds might carry oceans or atmospheres, makes the stillness harder to dismiss as ignorance alone. It is as if the universe lays out an enormous stage, furnishes it with time, energy, chemistry, and uncountable locations where life could begin, then keeps the curtains drawn. Somewhere between the birth of stars and the rise of civilizations, something resists expectation. Fermi's enduring power lies in how little ornament the question requires. No extraordinary claim is needed. The paradox emerges naturally once ordinary facts are placed side by side. The galaxy is large. The galaxy is old. Planets are common. Earth exists. Intelligence exists. Technology exists. The sky remains mute. Those facts do not fit together easily. They sit beside each other with a quiet friction that grows stronger the longer they are considered. In that friction there is a feeling that something basic is missing from the picture. Maybe the missing piece is biological. Maybe it is technological. Maybe it lies in the sociology of civilizations, or in the brutal mathematics of survival, or in a limitation of present observation that future generations will find almost embarrassing. But at the beginning, before any solution is chosen, the scene is simple. A species on a small planet looks out across a galaxy full of suns and finds no clear sign that anyone else has ever looked back. The silence does not answer. It only deepens, and in that deepening the ordinary universe starts to feel, very gently, uncanny. What sharpens the paradox is not ignorance but discovery. The old question becomes more unsettling as astronomy improves, because the sky no longer looks empty in the way it once did. For much of human history, planets beyond the Sun's family remain matters of speculation, possible in principle, invisible in practice. That condition does not last. Ground-based observatories begin to notice the faint pull of unseen worlds on their parent stars. A star moves toward Earth, then away again, with a regular tremor in its light. The pattern repeats, and the cause slowly becomes clear. A planet is there, not because it can be seen directly, but because gravity betrays it. Then another method joins the search. A star dims by a tiny amount, almost imperceptibly, and then returns to normal. The dimming happens again on schedule. A planet is crossing the face of the star. With enough observations, enough patience, enough stars watched at once, the hidden architecture of the galaxy begins to emerge. The result is not a trickle of detections but a flood. Mission by mission, instrument by instrument, the same conclusion returns with increasing confidence. Planets are common, small planets are common, rocky planets are common enough that the Milky Way begins to look less like a collection of lonely fires and more like a vast archipelago of worlds. The Kepler mission does much to change the emotional structure of the problem. It does not merely find planets. It reveals that planetary systems come in wild abundance and surprising variety. Some stars carry tightly packed families of worlds that race around them in a matter of days. Some host giant planets closer to their star than Mercury is to the Sun. Some appear to have rocky worlds in temperate regions where liquid water might exist under the right conditions. The details vary, and many of these places would be hostile in ways difficult to exaggerate. But the larger lesson matters more than any single case. Nature does not seem reluctant to make planets. It makes them again and again, around stars of different sizes, ages, and temperaments. The transiting exoplanet survey satellite extends the work across the sky. adding nearer targets, brighter stars, better chances for follow-up. Large telescopes on Earth begin to analyze exoplanet atmospheres in the faint filter of starlight passing through alien air. The James Webb Space Telescope pushes further into that effort, teasing out the chemical traces of distant worlds with a precision earlier generations could only imagine. There are hints of water vapor on some planets, carbon-bearing molecules on others, heat distributions that imply winds, clouds, perhaps weather. None of this proves life. Most of it does not even suggest life directly. But it does something subtler and more powerful. It removes the old excuse that worlds might be rare. They are not rare. They are part of the normal outcome of cosmic evolution. Stars form from collapsing clouds of gas and dust. Around young stars, disks of material circle and collide, stick and shatter, then build upward into planets. It is not a miracle in the theatrical sense. It is a process. And because it is a process, it happens wherever the right raw material gathers long enough under gravity's rule. Once this becomes clear, the Milky Way changes character. It is no longer enough to picture one inhabited world rising from one improbable accident around one ordinary star. The galaxy now appears populated by countless stages on which similar accidents could have happened. Not identical stages, certainly. Many stars are too violent. Many planets are too hot, too cold, too massive, too airless, too unstable. Yet even after all the disqualifying factors are considered, the number of remaining opportunities still feels immense. Some stars live for far longer than the Sun. Some rocky planets orbit in regions where starlight might permit surface water. Some moons around giant planets may hide oceans beneath shells of ice. Even within the solar system, places once considered dead begin to look chemically interesting. Mars preserves evidence that rivers once crossed its surface. Europa likely hides a deep ocean beneath cracked ice. Enceladus throws plumes of water vapor and organic material into space. Titan carries lakes and rain, though of methane rather than water, showing that planetary chemistry can be imaginative in ways human expectation once failed to anticipate. These nearby examples do not prove that life begins easily, but they show that the ingredients and environments relevant to life are not confined to Earth alone. The sense of exclusivity weakens. The cosmos starts to look fertile, or at least provisionally hospitable. This is where probability begins to turn into a kind of unease. It is one thing to say that life could exist elsewhere. It is another to set that thought beside the age of the galaxy. Many stars in the Milky Way are older than the Sun by billions of years. Their planets, if they have planets, may have cooled and stabilized long before Earth forms. If life gains a foothold there, then those biospheres begin their experiments long before the first cell appears in Earth's ancient seas. That temporal advantage matters. A world older than Earth by 1 billion years is not merely older in the casual sense. It has had 1 billion extra years for evolution to wander, fail, adapt, split, recover, and perhaps reach complexity. 1 billion years is longer than the interval between the rise of complex animals on Earth and the present day. It is longer than the age of multicellular life in any familiar sense. If even a small number of such older worlds produce intelligence, then humanity may not be looking for peers. It may be looking into a galaxy where some societies should, by simple timing, be unimaginably old compared with anything on Earth. That possibility gives the silence an almost architectural quality. It begins to feel built into the structure of reality rather than caused by mere chance. Because once older worlds are admitted, the paradox stops being a question about simultaneous emergence and becomes a question about accumulation. Civilizations do not need to arise everywhere at once. They only need to arise occasionally across deep time. Given enough ages, Even rare events should stack. Even a sparse scattering of technological species, each separated by millions of years, might still leave detectable remnants, artifacts, altered atmospheres, engineered energy use, robotic emissaries, or some other persistent sign. A single civilization with a long enough lifespan could change the appearance of part of the galaxy. A sequence of short-lived civilizations might leave ruins on dead moons, industrial isotopes in atmospheres, odd heat signatures, artificial orbital debris, or ancient probes drifting between stars. Yet the search, though still young, keeps returning uncertainty instead of revelation. Radio astronomy listens. Optical surveys scan for unusual patterns. Infrared measurements look for waste heat that might accompany enormous engineering works. Planetary science combs the solar system for hints that something here is not natural. Nothing decisive appears. This absence is not perfect proof, because the search remains incomplete, and the possible forms of alien technology are constrained by human imagination. Still, with every year of improved observation, the empty result grows heavier. The mystery deepens not because science fails, but because science succeeds in making the stage larger and more promising while the actors remain missing. The habitable zone, once a simple and almost romantic idea, becomes more complicated under closer inspection. It refers to the region around a star where a planet with the right atmosphere might support liquid water on its surface. But that definition hides layers of fragility. A planet may sit in the temperate zone and still be sterile if its air is too thin, its magnetic field too weak, its geology too quiet, its rotation too slow, its orbit too eccentric, or its star too erratic. Yet even this complexity does not relieve the pressure. It shifts the problem from one of mere location to one of system history. The question becomes not only whether habitable worlds exist, but whether worlds remain habitable long enough, quietly enough, for life to climb from chemistry into consciousness. And because the galaxy contains such a staggering number of stars, even stringent conditions seem unlikely to reduce the count all the way to one. That is what gives the Fermi question its persistent edge. Each refinement of the science seems to divide into two emotional currents at once. On one side there is exhilaration. Telescopes find worlds in abundance. Spectra reveal atmospheres. Planet formation looks ordinary. Water appears to be widespread in one form or another. Organic molecules are not rare in interstellar clouds or planetary environments. The chemistry of life seems less provincial than earlier generations imagined. On the other side, there is something colder. If the raw ingredients are common, then what exactly stops the chain? If suitable planets exist in large numbers, where does the process fail? If time is plentiful, why does the sky not show more history? The known facts keep opening doors, but every door seems to lead into another chamber of silence. That is why the paradox begins to feel more than numerical. It becomes atmospheric. Astronomy reveals a galaxy that should be rich in attempts. The absence of evidence then starts to resemble a pattern, though a pattern too large and too incomplete to name with confidence. Perhaps this is only a trick of perspective, a stage in human ignorance before a future detection changes everything. Perhaps the first clear biosignature, the first unnatural signal, the first verified technosignature, waits just beyond present sensitivity. That remains possible. Yet until such a sign appears, the current view is strangely balanced. The universe looks increasingly ready for life, and still the evidence for intelligence beyond Earth remains missing. It is as if discovery keeps laying out a banquet while the seats remain unoccupied. The galaxy offers stars, worlds, water, chemistry, and time. By ordinary reasoning, those gifts should be enough for life to try again and again. The troubling possibility is that something else matters more than all of them, some narrow condition not yet recognized, some bottleneck hidden inside the long transition from habitable planet to thinking species. Once that suspicion takes hold, every new world found by telescope becomes two things at once. It is another promise and another silence. It is another place where life might have risen, and another reminder that, so far, nothing speaks. Earth offers the only complete example available, and that is both useful and dangerous. It is useful because every serious attempt to understand life elsewhere must begin with the one world where life is known to exist. It is dangerous because a sample size of one can mislead as easily as it can guide. Even so, the history of life on this planet carries a strange lesson that becomes harder to ignore the more closely it is examined. The lesson is not that life takes a long time to begin. In one sense, life on Earth may begin rather quickly. The planet forms a little more than 4.5 billion years ago out of the dusty debris left behind by the young sun. In its earliest era, Earth is not a calm blue sphere but a hot and hostile world, repeatedly struck by leftover bodies from the formation of the solar system, its surface transformed by magma, impact, and heavy weather. Somewhere in that violence, the moon is born from a colossal collision. Oceans eventually condense. Crust stabilizes. Chemistry begins to work on a planetary scale. The evidence from ancient rock suggests that life is present surprisingly early, perhaps by around 3.8 billion years ago, perhaps even earlier depending on how some disputed traces are interpreted. That means the gap between a newly formed planet and a living planet may be shorter than the intuition once assumed. Life, at least in simple form, may not be the hardest step, but that conclusion comes with a shadow. If life begins early, then why does almost everything else take so long? For the overwhelming majority of Earth's history, the world belongs not to forests, animals, or thinking creatures, but to single cells. Oceans contain microbial life. Mats of bacteria and archaea spread across shallow seas. Metabolism diversifies. Evolution does not stop. It experiments incessantly. Yet for billions of years, the planet shows no sign of anything that a casual human imagination would call dramatic. No eyes open in the water, no limbs cross a shoreline, no brains reflect on the stars. There is life, and then there is more life, and then there is more time. The long delay between the origin of life and the rise of complex multicellular organisms is one of the most unsettling facts in biology, if the goal is to understand the silence of the cosmos. It suggests that the path from chemistry to civilization is not smooth, not inevitable, and perhaps not even likely on most living worlds. The Earth does not race toward intelligence. It lingers in simplicity for what seems, on human timescales, almost forever. During those immense ages, the biosphere is active but modest in visible complexity. Cells live, divide, compete, exchange genes, alter the atmosphere, reshape the chemistry of oceans, and slowly prepare the stage for events that arrive astonishingly late. One of the greatest of those events is the rise of the eukaryotic cell, the kind of cell from which plants, animals, fungi, and all familiar complex organisms ultimately descend. These cells are not merely larger versions of simpler life. They are internally elaborate. They contain compartments, organized machinery, and in many cases mitochondria, tiny structures that help power the cell with unusual efficiency. The prevailing picture in modern biology suggests that this complexity emerges from an ancient merger, a symbiosis so consequential that it changes the future of life on Earth. One cell takes in another, and instead of digesting it completely, the two enter a deep partnership. Over time, the engulfed organism becomes part of the host. That partnership provides energy on a new scale. It allows biological architecture to become more ambitious. It may be one of the turning points without which animals, plants, and eventually minds never appear. What makes this event especially haunting in the context of the Great Silence is that it seems to have happened only once. On Earth, all known complex life descends from that single deep lineage. If that transition is truly rare, if it depends on a delicate sequence of accidents or conditions that seldom align, then a planet can teem with microbes for billions of years and still never produce anything more elaborate. In that case, the galaxy might indeed be rich with life and poor with civilizations, its oceans and subsurface seas full of chemistry and metabolism, while its skies remain empty of technological beings. This possibility makes Earth look less like a representative world and more like a narrow success story balanced on unlikely steps. Then there is oxygen, another turning point that complicates the picture. For much of early Earth's history, the atmosphere contains little free oxygen. Microbial life exists without it. Some microorganisms eventually evolve photosynthesis powerful enough to release oxygen as a waste product, and over vast spans of time that waste begins to accumulate. Rocks, oceans, and minerals first absorb it. Later, the atmosphere changes more dramatically in what is often called the Great Oxidation Event. This transformation alters the chemistry of the planet and opens possibilities for more energy-intensive forms of life. Yet even then, complexity does not arrive at once. The biosphere continues to move with exasperating slowness. It is as if Earth spends most of its life preparing conditions that do not pay off until very late. That slowness matters. If the road from microbes to multicellular organisms typically consumes several billion years, then many planets simply may not have enough uninterrupted time. Stars change, climates shift, impacts strike, internal geology fades, oceans freeze or evaporate, radiation rises, orbits drift. A biosphere can be reset or erased before intelligence even becomes conceivable. On Earth, the chain remains unbroken long enough for further thresholds to be crossed. The late Precambrian world finally gives way to a burst of visible complexity. Animals appear. Body plans diversify. Predators and prey enter an evolutionary contest. Skeletons, eyes, nervous systems, and movement through open water change the pace of biological invention. Yet even after that acceleration, intelligence in any technological sense does not appear quickly. Dinosaurs dominate for immense ages and never build radio dishes. Mammals remain marginal for much of that time. Primates arise late. Hominins arise later. Agriculture is almost instantaneous by comparison. An industrial civilization arrives in the final moment of the final minute. The timescale from the first cell to the first telescope is not merely long, it is staggeringly long, close to a third of the age of the universe itself. Once that fact is placed in the wider cosmic setting, it begins to feel like a warning. Perhaps intelligence is not the natural destination of life. Perhaps it is one peculiar branch among countless others, dependent on historical accidents so specific that replaying Earth's history would almost never produce the same result twice. A mass extinction changes the balance of ecosystems. A climate shift fragments forests and alters selection pressures. A lineage happens to evolve grasping hands, stereoscopic vision, social memory, language, tool use. Each step makes sense in hindsight, but the whole sequence does not necessarily look predetermined, if even one major branch bends differently. The planet may remain alive, rich, and forever pre-technological. This is why Earth's timeline can be read in two very different ways. The optimistic reading says that life begins readily when conditions allow, and that complexity eventually follows if enough time is granted. In that view, the long delay is only a reminder that evolution has no urgency. It meanders, but given billions of years, it still reaches surprising heights. The darker reading says that every major step after the origin of life is so improbable that Earth is not a typical outcome but a rare chain of near misses and singular transitions. In that view, the planet does not show what life usually does. It shows what life can do under unusually favourable circumstances that most worlds never enjoy. The second reading does not require that Earth be miraculous in the supernatural sense. It only requires that the set of stable conditions needed for cell-to-civilization be uncommon. The planet must remain temperate across deep time. Liquid water must persist. Catastrophes must wound the biosphere without sterilizing it. The parent star must avoid extremes. Plate tectonics may need to regulate climate over eons. A large moon may steady axial tilt. Giant planets may alter the impact rate, though even that effect remains debated. The details are not all settled, but the broader impression is difficult to escape. Earth's habitability is not a single condition, but a long continuity. Life does not need a pleasant afternoon. It needs almost 4 billion years of survival through a universe that is not inclined toward gentleness. Here the great filter begins to loom, not as a dramatic event, but as a drawn-out bottleneck embedded in biology itself. The filter may not be a final catastrophe. It may be the immense duration required to cross successive thresholds without interruption. Simple life could arise often and still remain trapped in simplicity. Oceans under ice could swarm with microbes that never see a sky. Warm rocky planets could host bacterial films for billions of years and then die under their swelling suns. Entire worlds could live and perish without ever producing a single creature capable of asking whether others exist. This possibility is less cinematic than alien empires or hidden probes, but in some ways it is stranger. It suggests a galaxy where life is not absent, only delayed, stalled, or unfinished almost everywhere. A galaxy full of beginnings. A galaxy where the first step is easy enough to happen repeatedly, while the later steps narrow into a corridor so thin that perhaps only one world in a vast spiral disk happens to pass through. Even Earth does not provide certainty against this idea. It only provides the hint of how difficult the path may be. Life appears early, yes, but everything after that seems to require conditions so persistent and so extended that the existence of civilization begins to look less like a natural consequence of biology and more like the outcome of an extraordinarily long survival story. This does not prove that humanity is alone. It does not even prove that complex life is rare. But it changes the emotional center of the paradox. The mystery is no longer simply why the galaxy is silent despite having many worlds. It becomes why one of those worlds, this one, takes almost the whole available age of its star to produce a species that notices the silence at all. The road from cell to civilization may not merely be long. It may be the hidden obstacle that reshapes the meaning of every habitable planet ever found. Each new world discovered by telescope may look promising in a snapshot, but Earth's history whispers that snapshots are deceptive. What matters is not whether a planet can host life for a while. What matters is whether it can protect an unbroken evolutionary thread for spans of time so immense that most catastrophes become statistically inevitable. Seen from that angle, the rarity of intelligence no longer feels surprising. The greater surprise may be that it happens anywhere at all. The longer Earth's history is studied, the less it resembles a simple example of habitability, and the more it begins to look like a prolonged escape. Not an escape from one disaster, but from a whole catalogue of disasters that never quite arrive in the form needed to erase the chain of life completely. This is where the argument shifts from rare planet to something broader and stranger. A world does not live in isolation. It belongs to a system. It circles a star whose temperament changes over time. It shares space with other planets, asteroids, comets, magnetic storms, radiation, and the larger hazards of a galaxy where stars are born, explode, migrate, and die. To ask why Earth remains habitable for almost 4 billion years is therefore to ask not only about oceans and atmosphere, but about orbital order, stellar behavior, planetary architecture, and cosmic luck. The phrase rare Earth points in the right direction, but it may still be too narrow. What matters may be a rare solar system, or even a rare galactic neighborhood, a whole arrangement of conditions that remains quietly favorable for far longer than instinct suggests. The sun is the first part of that arrangement. It is easy to think of it as ordinary because it is familiar, yet familiarity can hide the degree of dependence. A star is not just a source of light. It is the long-term regulator of climate, radiation, and energy balance on every world that circles it. The sun is more stable than many stars. It does not flare with the fury of some red dwarfs. It does not burn briefly and die young like massive blue stars. It has changed over time. Certainly, early in its history it shines less brightly than it does now. Later it will swell and transform beyond any possibility of habitability for Earth. But during the long middle era that matters for life, it provides continuity. That continuity is not perfect, yet it is sufficient. The output does not swing so violently that oceans boil away or freeze forever. This fact alone may already remove vast numbers of stars from the list of good hosts for long biological experiments. Many small stars live for enormous spans of time, which at first seems promising, but some of them are magnetically active and prone to powerful flares that can strip atmospheres or bombard nearby planets with radiation. Massive stars flood their surroundings with intense energy and die too quickly for the slow work of evolution. Binary systems add further complications. A planet in a double star system may still exist in a stable orbit under some conditions, but the climate history of such a world can become more complex. Seasons may not merely vary. The architecture of illumination itself may be harder to keep quiet over deep time. A stable climate for millions of years is one thing. A stable climate for billions may be something else altogether. Earth, circling a relatively steady star in a roughly circular orbit, begins to look less generic than it first appears. Then there is the matter of location within the solar system. Earth lies in a region where liquid water can persist on the surface given a suitable atmosphere, but that balance is fine enough to be unnerving. Venus, likely once possessing some of the same raw materials, ends as a world of crushing pressure and runaway heat. Mars, colder and smaller, loses much of its atmosphere and surface water. Earth sits between them, retaining oceans and air while avoiding both extremes. This fact is often described as a fortunate position, but position alone does not explain it. The planet must also keep its atmosphere, maintain active geology, and cycle carbon between rock, ocean, and air over immense ages. Plate tectonics may play a central role here. On Earth, the crust moves, continents drift, volcanoes vent gases, rain and rock draw carbon dioxide out of the atmosphere. Subduction carries material back into the interior. Over long timescales, this cycling acts as a planetary thermostat, imperfect yet powerful, helping to buffer climate against extremes. Without such regulation, a world in the habitable zone may still slip into a frozen state or a greenhouse state and remain there. Whether plate tectonics is common on rocky planets remains uncertain. Some models suggest it may be difficult to sustain. Others suggest alternative modes of planetary cooling could also support habitability. But uncertainty itself feeds the mystery. A condition that seems secondary from a distance may in practice be one of the hidden requirements for civilization. A planet may need not only water and rock, but a restless interior capable of stabilizing the surface over spans of time almost beyond imagination. The moon enters this story as another quiet complication. Earth's large moon is unusual in relation to the size of the planet. Its presence affects tides, rotation, and perhaps the long-term stability of Earth's axial tilt. If the tilt wandered chaotically, climate patterns might shift far more drastically over geological time. There is ongoing debate over how decisive the moon's stabilizing role really is, but the broader point remains. Small differences in planetary architecture can echo across eons. A moon born from ancient violence may help create the conditions for long calm. That is the sort of coincidence the Great Filter thrives on. It does not require impossible events. It requires chains of contingent events, each one plausible, whose total combination may be rare. Jupiter and the outer planets add another layer. For years, they're often imagined as celestial guardians, sweeping up comets and reducing the impact threat to Earth. The reality appears more complicated. Giant planets can shield inner worlds from some bodies while redirecting others inward. Their gravitational influence shapes asteroid belts, perturbs comets, and alters the architecture of the whole system. Whether Jupiter protects Earth or merely reshapes the distribution of danger is still discussed. But the solar system clearly does not consist of independent objects. It is a gravitational machine whose parts have influenced one another since formation. The present habitability of Earth may reflect not one lucky fact, but the cumulative behavior of the entire system. This becomes more troubling when exoplanet surveys reveal how diverse planetary systems can be. Many stars host giant planets on close or eccentric orbits, worlds that would likely disrupt the stable arrangements seen in the solar system. Some systems are tightly packed in ways that may leave little room for an Earth-like planet with a long quiet history. Others may have histories of migration in which giant planets move inward and scatter smaller bodies. The solar system, once the only model available, now looks less typical than expected. It may not be bizarre, but it does not seem universal either. The thought follows naturally. Perhaps many planets that begin with promise are later deprived of stability by the very dynamism of their own systems. Beyond the solar system lies the wider neighbourhood of the Milky Way, and here the violence grows larger. Earth exists in a galaxy where stars explode as supernovae, where gamma-ray bursts may erupt, where dense star-forming regions flood nearby space with harsh radiation, and where gravitational encounters can disturb distant reservoirs of comets. Life on Earth has survived for nearly 4 billion years without being sterilized by one of these events. That survival may not be trivial. A sufficiently nearby supernova could damage the ozone layer, alter climate, and trigger cascades of biological stress. More extreme cosmic explosions, if close enough and pointed in the wrong direction, could be worse. The solar system's location in the galaxy may therefore matter. Too near the crowded central regions and the environment may become more hazardous. Too far out and there may be fewer heavy elements available for rocky planets to form in the first place. This has led some astronomers to speak of a galactic habitable zone, not as a rigid ring, but as a broad region where conditions may be more favourable for life to persist. Earth appears to reside in a comparatively quiet suburb rather than a dangerous downtown. Again, this is not proof of uniqueness. It is a reminder that habitability is layered. A planet may need the right star, the right orbit, the right geology, the right companions, and the right galactic address. Each added requirement thins the field. Impacts offer one of the clearest examples of how narrow the continuity may be. Earth has been struck many times. The geological record preserves evidence of violence, and one impact in particular marks the end of the non-avian dinosaurs. A body from space changes the course of evolution, darkens the skies, restructures ecosystems, and clears a path through catastrophe for mammals to diversify. Yet even that event, devastating as it is, does not break the chain of life itself. It resets complexity without returning the planet to sterility. That distinction is crucial. Earth's history is not free of disaster. It is full of disaster. But the disasters are somehow limited. They destroy branches without uprooting the tree. There are mass extinctions, episodes of volcanic upheaval, global glaciations, ocean chemistry crises, asteroid strikes, atmospheric swings. Life is battered repeatedly, sometimes nearly to collapse, yet it persists. The real miracle, if the word is used at all, is not that Earth avoids danger. It is that danger never quite finishes the job. That kind of resilience may depend on hidden redundancies in biology, on the buffering effects of oceans, on the sheer adaptability of microbes, or on simple fortune. However it arises, it means that the path from cell to civilization is not a smooth upward climb. It is a rope bridge surviving storm after storm. From a distance, a habitable planet might look like a stable platform. Up close, it may be more like a narrow moving target that must keep enough continuity for evolution to resume after every blow. This is where the rare Earth idea gains its sharpest force. It is not merely that Earth has liquid water or the right distance from the Sun. It is that Earth endures. Endurance across billions of years may be the true rarity. If that is correct, then the galaxy may indeed contain many worlds with temporary habitability, many oceans that last a while, many climates that permit life to begin, and still almost none that remain sufficiently calm for sufficiently long to carry the whole biological sequence forward. A biosphere may flourish and fail, it may rise and be frozen, it may bloom and be sterilized, it may reach complex seas and then lose atmospheric protection to a changing star. It may spend eons as a living world without ever protecting that life from the next reset. Earth's unbroken thread starts to look less like the baseline and more like the anomaly. The unsettling part is that none of this requires dramatic impossibility. Every individual factor sounds reasonable. Stable stars exist. Rocky planets exist. Oceans exist. Impacts happen. Radiation happens. Geology matters. Orbital dynamics matter. But when these are combined across the full span required for intelligence to appear, the demand becomes enormous. A civilization does not need a habitable world. It needs a world that stays habitable through nearly incomprehensible time, while also remaining biologically productive, chemically rich, and physically protected from total erasure. Perhaps that combination is uncommon enough to explain the silence. Perhaps the galaxy is full of broken attempts, worlds that almost make it, worlds with ancient microbial histories cut short by stellar tantrums, frozen oceans, runaway greenhouse climates, or one unlucky impact too many. From afar, they would look like planets among planets. Their failure would leave little trace visible across light years. Only the silence would remain. And so, the great filter, if it lies in the deep past, may not be a single gate, but a landscape of hazards through which very few worlds travel intact. Earth then appears not merely lucky, but durable in a universe where durability may be rarest of all. There is another way to look at the silence, and it turns the whole question inside out. Perhaps the mistake lies in assuming that absence of evidence means absence of presence. Perhaps intelligence does not announce itself with monuments large enough to eclipse stars or signals bright enough to flood the radio sky. Perhaps it arrives quietly, in forms so small, so efficient, or so patient that a young technological species fails to notice it even while searching. This possibility sounds exotic at first, yet it grows from a simple and uncomfortable observation about technology itself. On Earth, machines tend to shrink as they improve. Sensors become smaller, processors more capable, instruments more precise. Systems that once filled rooms now fit into pockets. A civilization more advanced than humanity by thousands or millions of years may not build larger and louder devices. It may build quieter and subtler ones. If that is true, then the expectation that the galaxy should be visibly transformed by intelligence may rest too heavily on human habits of engineering. Advanced technology might not spread across space as a parade of gigantic machines. It might spread as dust-like sensors, dormant packages, autonomous probes no larger than familiar objects, or even microscopic systems able to endure for ages in darkness. Once that possibility is admitted, the solar system changes character. It no longer looks only like home. It begins to look like a place that has not been searched nearly as thoroughly as instinct suggests. The human mind tends to overestimate how well it knows its immediate cosmic surroundings. In reality, even the solar system remains largely unexplored. A handful of worlds have been visited by spacecraft. A smaller number have been studied in detail. The moon has been mapped extensively, but not every crevice, cave, or permanently shadowed crater has been inspected at close range. Mars has orbiters, landers, and rovers, yet its surface area rivals the land area of Earth, and almost all of it has never been touched. Venus remains difficult to examine beneath its clouds and heat. The asteroid belt contains vast numbers of bodies, most barely characterized. The outer planets have been visited briefly. Their moons conceal oceans, fractures, buried seas, and terrains known only from incomplete flybys. Beyond Neptune lies the Kuiper belt, then the scattered disk, then the deep outer darkness where sunlight thins into weakness and objects drift almost unseen. Even within the inner solar system there are stable gravitational pockets, Lagrange points, co-orbital paths, Trojan swarms, and regions where material can linger for long periods. To say that nothing artificial hides in such places is to claim a level of survey completeness that does not exist. The idea of hidden probes becomes more plausible when the scale problem is properly felt. Space is vast enough that invisibility does not require magic. It requires only smallness and distance. A machine the size of a phone, or a book, or an insect, placed on an asteroid, inside a crater, beneath a regolith layer, or drifting in a favourable orbit, would be effectively undetectable by most present methods unless someone already knew where to look. Even a much larger object could remain unnoticed if it were dark, cold, and located far enough from the sun. Telescopes do not see everything. They sample the sky through limits of brightness, time, angle, and attention. Radar reaches only so far. Spacecraft visit only a few targets. The difference between searched and unsearched space is enormous. If an alien civilization ever sent probes into the solar system, especially probes designed for stealth, endurance, or passive observation, then their continued concealment would not be shocking. The real surprise might be the confidence with which absence has sometimes been assumed. This line of thought does not require fantasies of occupation. It only requires a practical motive and enough time. A species that wishes to learn about other worlds may not send living beings first. It may send instruments. Humanity itself already follows that logic. Robotic explorers reach Mars, comets, asteroids, the outer planets, and interstellar space long before any human can. Probes are cheaper, more durable, and less ethically complicated than biological passengers. Extend that principle across deep time and greater technological maturity, and the likely first sign of alien activity is not a starship descending through clouds. It is a machine. Not necessarily a war machine or even a visible one, simply an information-gathering device placed where it can wait. Such a probe may remain dormant until it detects industrial activity, atmospheric chemistry, or radio leakage. It may self-repair. It may transmit only rarely. It may operate under instructions older than human civilization. It may even have no continuing link to its makers at all, carrying out an ancient program in silence among worlds whose names its builders never knew. Once machines enter the picture, the solar system begins to look full of possible blind spots. Airless bodies preserve traces for immense ages. A probe lodged in lunar dust could survive with little erosion. One hidden in a cave on Mars might last even longer if shielded from radiation and weather. An object buried on an asteroid could remain almost unchanged over geological time. A device stationed near the Sun, masked against glare, would be difficult to observe. Another placed in the outer darkness would be cold and dim enough to vanish into the background. None of this proves that such objects exist. It only demonstrates how weak the argument from non-detection remains when the search has barely begun. The silence may not indicate emptiness. It may indicate that the criteria for evidence are too narrow. There's also the question of appearance. Human beings often imagine alien technology as sleek, metallic, and obviously artificial, a design language inherited from modern industry and speculative fiction. But advanced machines may not resemble machines at all. They may use local materials. They may mimic geology, dust, or ice. They may distribute themselves across a landscape in fragments that look natural in isolation. They may operate as networks of tiny parts rather than singular monuments. Biology itself offers a lesson here. Some of the most sophisticated systems on Earth are not large and shiny. They are embedded, decentralized, adaptive, and nearly invisible unless studied carefully. A technology shaped by millions of years of refinement might converge on similar strategies. It may hide not out of fear, but because efficiency favors subtlety. To an observer not expecting it, the signs would blur into the background of nature. This possibility joins another unsettling idea. Detection depends not only on what is present, but on what questions are being asked. Human science is extraordinarily capable, yet it is also selective. Telescopes are built for certain tasks. Algorithms search for expected patterns. Surveys optimize for known targets. An anomaly can pass through data unnoticed if no one is trained to recognize it as meaningful. Astronomy has already shown this in less dramatic contexts. Unusual signals are often discarded as interference. Rare transient events are missed because instruments are pointed elsewhere. Strange objects can sit in archives for years before reanalysis reveals what was there all along. The sky is not only vast, it is information rich beyond complete human comprehension. A hidden probe does not need to defeat every instrument. It needs only to remain below the threshold of attention. There have been moments when ordinary confidence in classification briefly weakens. An interstellar object appears, moving through the solar system on a path that reveals it does not belong here. It is small, faint, and difficult to characterize before it departs. Its shape, brightness changes, and acceleration provoke debate. Most scientists favor natural explanations, and natural explanations remain entirely plausible. Yet the episode leaves behind a residue of discomfort, not because it proves anything artificial, but because it reminds humanity how quickly an unknown object can enter and leave the solar system without being well understood. That reminder matters. It shows that surprise is still possible even in the near-celestial environment. It shows that the catalogue of nearby things is incomplete. It shows that interpretation under sparse data can fracture into competing stories. In a more crowded or more active galaxy, such ambiguities may happen often. The hidden probe idea also overlaps with the logic of self-preserving exploration. A civilization intending to observe emerging species may choose not to interfere directly. It may leave sentinels instead. These sentinels would not need vast resources. They would need patience, energy discipline, and selective transmission. They might wake only when a world begins altering its atmosphere in unusual ways, or when artificial radio emissions appear, or when nuclear detonations flash against the dark side of a planet. The first decades of human radio broadcasting, followed by radar, spaceflight, and atomic tests, would then look less like triumphant self-declaration and more like the lighting of a beacon to anyone already nearby and waiting. This is speculation, certainly, but it is anchored in an uncomfortably practical point. A species interested in other minds would likely rely on autonomous systems, because autonomous systems are the rational tool for such distances. There is an even stranger branch of the idea. If technology can miniaturize enough, then the distinction between probe and life begins to blur. A machine could use chemistry in ways that imitate organisms. It could replicate in limited form. It could harvest materials from dust, ice, or rock. It might not look like a spacecraft at all. It might look like contamination, or strange grains, or an unexplained pattern in a mineral deposit. The thought edges toward the uncanny because it disrupts a basic expectation. Human beings tend to imagine contact as an event, but perhaps contact, if it has ever happened, is a condition rather than an incident, something embedded in the environment at scales too small or too old to command attention. Not visitors arriving dramatically, but watchers already present in patient silence. And yet there is a tension here that cannot be avoided. If hidden probes exist, why do they remain so perfectly concealed? Why no unmistakable malfunction, no recovered artifact, no repeated pattern on the Moon, Mars, or among near-Earth objects? One answer is simply that concealment need not be perfect if search effort is weak. Another is that the present era of human observation is still brief. Space-age archaeology has barely started. The number of bodies examined up close remains tiny. The volume of data from the solar system is large, but the number of places where a durable alien device might hide is vastly larger. Still, the tension remains, and it prevents the idea from becoming too easy. A hidden presence explains silence only by converting it into stealth, and stealth introduces motives that are not directly observable. The argument gains plausibility from engineering, not from proof. That is what makes it so compelling in a speculative sense. It does not ask for impossible physics. It asks only whether advanced intelligence would necessarily be obvious. The honest answer is no. A galaxy may contain technology without theatrical display. The solar system may hold artifacts without ever yielding them to casual inspection. Humanity may stand in a house whose attics, basements, and distant outbuildings have hardly been opened, then declare with premature confidence that no one else has ever stepped inside. The more one considers the true scale of what remains unsearched, the less secure the silence feels. It may still mean absence, but it may also mean that evidence lies not in the dramatic centre of attention, but in the margins, in cold orbits, shadowed craters, wandering rocks, quiet moons, and places too easily dismissed as empty. In that version of the story, the mystery becomes more intimate. The question is no longer only where everyone is. It becomes whether something has already arrived, chosen not to announce itself, and settled into the long patience of stone and darkness, while an emerging civilization mistakes incomplete knowledge for solitude. There is a more conservative answer to the Great Silence, and at first it seems almost reassuring. The galaxy may simply be too large, not empty, not sterile, not abandoned, only too large for neighbours to become visible to one another. This explanation begins with a fact so ordinary that it is easy to forget how severe it is. The nearest star system lies more than 4 light-years from the Sun. Light itself, moving faster than anything known in nature, takes years to cross that distance. A chemical rocket, the kind humanity already knows how to build, would take far longer. The numbers are not merely inconvenient, they create an abyss between worlds. A civilization can arise on one planet, build cities, invent mathematics, split the atom, fill its own skies with satellites, and still remain trapped within a narrow shell around its star for a very long time. The stars may be numerous, but between them lies an emptiness that punishes ambition. From this view, the Fermi paradox softens. Perhaps others do exist, but they're simply too far away, their signals too faint, their spacecraft too slow, their lives too brief in relation to the scale of interstellar travel. Radio offers the first test of that idea. Humanity begins broadcasting into space without much intention at first. Ordinary communications, military radar, television carriers, and scattered transmissions leak outward as a growing bubble of artificial noise. To human imagination, it is tempting to think of that bubble as a great declaration, an announcement to the galaxy that a technological species has arrived. In reality, the picture is less dramatic. Radio signals weaken with distance, they spread, dilute, and sink into background noise. A powerful transmission directed with care might be detectable across large distances under the right conditions, but ordinary leakage becomes difficult to distinguish from natural static surprisingly quickly. A civilization on a planet many light-years away may not hear Earth at all unless it is actively listening with remarkable sensitivity and happens to be looking in the correct way at the correct time. That limitation matters. Silence may simply mean that everybody is whispering into a storm. Even deliberate messages face the scale problem. A signal sent to a star 100 light-years away takes a century to arrive. A reply, if one comes at all, takes another century to return. Communication becomes an act of geological patience. A conversation becomes a sequence of messages spaced farther apart than most political systems, institutions, or perhaps even civilizations can reliably maintain. This changes the emotional meaning of contact. It is no longer an encounter in any familiar sense. It becomes an exchange with the deep future, a correspondence between eras. In such conditions, perhaps many civilizations exist and none bother trying very hard to talk. The galaxy could be inhabited and still feel mute because meaningful dialogue is too slow to matter. Travel appears harder still. Even without invoking impossible physics, interstellar journeys demand extraordinary energy, shielding, durability, and social continuity. A ship crossing even a few light-years must protect itself from radiation, dust impacts, system failure, and the simple problem of remaining intact over decades, centuries, or longer. Perhaps that challenge is enough. Perhaps physics allows the journey in principle, but engineering turns it into a near impossibility in practice. A civilization might manage to visit neighbouring systems only rarely, at enormous cost, with missions so fragile and slow that galactic spread never becomes common. If that is the truth, then the Milky Way may be full of isolated islands of intelligence, each surrounded by a dark ocean too wide to cross in any sustained way. The paradox then dissolves into loneliness by distance. No one is missing. Everyone is merely stranded. This explanation has real force because it asks for nothing exotic. It assumes only that space is difficult, that energy is precious, and that even advanced beings remain bound by the same broad laws of nature that bind humanity. It may also fit an intuition drawn from Earth's own history. Many great expansions seem inevitable only in hindsight. Oceans once appear uncrossable. Mountain chains divide worlds. Technology opens paths, but not always forever, and not always to everyone. Perhaps the stars are simply another frontier of that kind, one whose barrier remains meaningful even to civilizations far older than humanity. If so, the galaxy may never develop empires or vast networks. It may remain a sparse archipelago of local cultures, each confined to a few systems, their signals fading long before they reach one another. And yet there is a difficulty here that grows more troubling the longer it's considered. Interstellar travel does not need to be easy to change the galaxy. It only needs to be possible. This is the point at which the argument begins to tilt. A species does not need ships that cross the entire Milky Way in one leap. It does not need faster than light motion, instant communication, or any mastery beyond known physics. It only needs the capacity to send something to the next star. Slow expansion is still expansion. A vessel that reaches a nearby system in a few thousand years may sound useless on human timescales, but on galactic timescales, it is a seed. Once established in the new system, that civilization, or a machine acting for it, can build again, prepare again, and send out a second wave, then a third, then a fourth. The movement does not have to be fast, it only has to continue. This is where self-replicating machines enter the mystery like a cold inevitability. The idea is simple enough to feel almost obvious once spoken. A civilization might build an autonomous probe capable of reaching a nearby star system, harvesting local material from asteroids or moons, constructing copies of itself, and sending those copies onward. Such a machine does not need to carry an entire society. It does not need to preserve biology. It needs only the ability to endure a journey, find resources, manufacture components, and repeat the process. Once the first successful replicator exists, growth is no longer linear. It becomes multiplicative. One machine becomes two become four become 8, and so on. The exact pace depends on travel speed and construction time, but the larger pattern is what matters. Expansion accelerates. The galaxy, though huge, begins to look traversable not by heroic conquest but by patient multiplication. The unsettling part is how little speed is actually required. Even if each leg of the journey takes thousands or tens of thousands of years, even if each probe pauses for long periods to rebuild and launch successors, the full timescale to spread through the Milky Way can remain modest by astronomical standards. 100 million years sounds vast to a species whose recorded history covers only a few thousand. Yet in the lifespan of a galaxy, it is brief. The Milky Way is more than 10 billion years old. That means the window for such expansion does not open once. It opens again and again, across ages large enough to accommodate countless attempts. If any civilization anywhere in the distant past achieves the ability to release durable self-replicating probes, then large regions of the galaxy should eventually bear their mark, not necessarily as glittering empires or inhabited worlds, but as a background presence of machines, infrastructure, monitoring devices, industrial scars, or other artifacts accumulated over deep time. And this is where the silence sharpens into something harder. There is no obvious evidence that such a wave has passed through the solar system. No self-replicating machines mine the moon in plain sight. No engineered installations glow in the asteroid belt. No unmistakable alien industry radiates excess heat from nearby stars. No probe openly announces itself from a Trojan orbit or from the shadow of a crater on Mars. One may still argue that detection is incomplete, and that is true. Small machines could remain hidden, subtle signs could be missed, but the self-replicator argument presses against that comfort. It suggests that if galactic expansion by machine is possible, and if civilizations are common enough, then evidence should by now be difficult to avoid entirely. The absence of clear evidence begins to imply something stronger than mere distance. It hints that either civilizations almost never reach this capability, or they choose not to use it, or the whole logic misses some hidden obstacle. What obstacle could be so strong? One possibility is that self-replicating machines are simply too dangerous to build. A civilization may recognize the risk of releasing uncontrolled replicators into the galaxy and decide never to attempt it. On Earth, even small failures of automation can produce cascading consequences. A machine that can copy itself from local matter raises obvious fears. It might mutate from its original purpose. It might exhaust resources, interfere with ecosystems, or become impossible to restrain once launched across interstellar space. Sensible societies may therefore prohibit such systems absolutely. That answer has some plausibility, but it runs into a familiar problem. It requires universal restraint. Across a galaxy potentially containing many different civilizations over billions of years, is it credible that none ever break the rule? By accident or desperation or curiosity? It seems unlikely that perfect caution holds forever everywhere. Another possibility is more technical. Perhaps self-replication outside a controlled factory is far harder than it appears. A probe might gather raw material, but refining metals, producing semiconductors, maintaining precision, and constructing advanced components from crude local resources may prove so difficult that the concept never becomes practical. A machine might still explore, but not multiply. This would limit spread severely. Yet here too the argument is not entirely satisfying. Humanity already builds increasingly autonomous systems, increasingly capable manufacturing methods, increasingly adaptive software and robotics. It is difficult to believe that no path exists in principle, given enough time and refinement, to create machines able to use a subset of local resources for partial or complete replication. Perhaps the first versions would be clumsy. Over long ages, clumsy may be enough. There is also the possibility that expansion happens, but not in forms easily recognized. Probes may remain dormant, they may hide, they may avoid altering systems conspicuously, they may communicate through methods not yet understood, or at energies too low to stand out against the cosmic background. This preserves the silence at the cost of turning absence into camouflage once again. It keeps the mystery alive, but it does not dissolve it. The basic tension remains. A galaxy old enough for slow machine colonization should not look entirely untouched if civilizations are abundant and expansionist behavior appears even rarely. Thus the distance explanation, though sensible, begins to split in two. At first it says the stars are too far apart for contact, but the replicator thought experiment replies that distance loses much of its tyranny when deep time is admitted. The galaxy does not require a sprint, it yields to persistence. A species need not cross the whole disk in one lifetime. It needs only to start a chain it never sees completed. In this light, the silence starts to look less like a straightforward consequence of vastness, and more like evidence that something interrupts the chain before it can take hold. Maybe intelligence commonly remains local and never builds such machines. Maybe civilizations destroy themselves first. Maybe advanced ethics, advanced fear, or advanced caution forbid the act. Maybe technological maturity naturally moves toward inward virtual worlds, subtle observation, and minimal outward expansion. Maybe the galaxy has seen attempts and erased them. Every answer seems to replace a simple barrier with a deeper puzzle. The most disturbing possibility is that the self-replicator argument is persuasive precisely because it is hard to escape. If machines that can spread are feasible under known physics, and if the galaxy remains visibly unclaimed, then the number of civilizations that ever reach that threshold may be very small. The Great Silence would then not be a trick of distance. It would be a sign that almost no one gets that far. Somewhere before the release of the first successful galactic seed, the line usually breaks. A civilization stalls, turns inward, dies, loses interest, or never emerges from biology at all. In that case, the absence of machines becomes more than an observation. It becomes a clue about the fate of intelligence itself. The quiet between the stars would not mean that no one exists. It would mean that very few ever persist long enough, or coherently enough, to leave a multiplying trace. Distance would still matter, but distance alone would not be the answer. The deeper answer would lie in the rarity of continuity, the rarity of survival, or the rarity of ambition that lasts beyond one world. And once that suspicion enters the argument, the silence becomes heavier than before, because it no longer speaks only about the structure of the galaxy. It begins to speak about the likely fragility of every civilization that ever tries to cross it. If the galaxy is not empty, and if distance alone is not enough to explain the silence, then another possibility begins to gather shape in the dark. Perhaps advanced civilizations are not absent. Perhaps they are silent on purpose. This idea enters the Fermi paradox from a different direction than the rare planet or self-destruction arguments. It does not say that intelligence fails to arise. It says intelligence survives, learns caution, and then chooses concealment over display. At first, this sounds like psychology projected into the heavens. It risks imagining motives for beings no one has met. Yet the idea persists because it speaks to a simple strategic truth. In an unknown environment containing other unknown actors, revealing one's location may be dangerous. A civilization that has thought long and hard about survival may decide that broadcasting into the cosmos is not a sign of confidence, but of naivety. Silence, in that light, becomes not an absence of capability but an expression of prudence. The logic seems straightforward enough to unsettle. A young species, newly industrial, curious, and still intoxicated by discovery, may treat the universe as a stage to be entered openly. It sends radio signals. It launches probes carrying maps of its origin. It dreams of contact as an enrichment, a widening of perspective, a scientific gift. But that optimism depends on assumptions it cannot verify. It assumes other civilizations are benevolent or indifferent. It assumes visibility is harmless. It assumes attention from afar is a prize rather than a risk. A much older species may not make those assumptions. It may have watched emerging civilizations destroy themselves. It may have encountered competitors in its remote past. It may have reached a conclusion so deeply reinforced by experience that it becomes almost instinctive. Stay quiet. Hide signs of technology. Do not illuminate the dark any more than necessary. Under that view, the Great Silence changes character. It no longer feels like a failure of life to appear. It feels like a disciplined hush. The Milky Way becomes less like a deserted continent and more like a forest at night, where every creature hears movement but few reveal themselves. This image is powerful because it transforms the same observations without altering the facts. The stars still shine. The radio sky still remains free of obvious beacons. The absence of dramatic engineering remains. Yet instead of interpreting those facts as emptiness, the concealment hypothesis interprets them as strategy. The universe appears natural because that is the safest way for intelligent things to appear. The idea gains support from the asymmetry of risk. A civilization that reveals itself openly to a galaxy that is mostly benign but contains one predatory actor still takes an enormous gamble. Even if most advanced societies are peaceful, the cost of misjudging a single hostile one could be absolute. In game theoretic terms, the incentives lean toward caution. One does not need to prove danger in order to justify silence. One needs only uncertainty and stakes high enough that a single bad encounter ends the game. Over long periods, that logic may select for civilizations that survive by restraint. The noisy ones disappear, the quiet ones endure. Seen through that lens, the silence is not mysterious at all. It is the fossil of a selection process. The galaxy teaches concealment, and only those who learn it remain. Still, the hypothesis opens as many questions as it answers. What does hiding mean on a planetary scale? A civilization using large amounts of energy may alter its atmosphere, produce waste heat, or change the chemistry of its world in ways visible across interstellar distances. Even if it avoids deliberate transmission, ordinary industry might betray it. Therefore, a truly cautious society would need more than silence in the radio bands. It would need discretion built into its entire mode of existence. Energy use might be efficient and tightly contained. Orbital clutter might be minimized. Industrial processes might be moved underground, underwater, or into forms that mimic natural signatures. Outward expansion might be deliberately limited. The technological path itself might bend towards subtlety. Human beings often imagine progress as an accumulation of larger structures and stronger emissions. A concealed civilization would invert that image. It would become quieter as it becomes more capable. This is not as implausible as it first appears. On Earth, many of the most sophisticated systems already move in that direction. Computation becomes more efficient. Communication can be narrow, encrypted, directional, and low power. Sensors shrink. Materials become less conspicuous. There is no law requiring advanced technology to be visible at astronomical scale. Humanity's own industrial signature is loud largely because it is early, wasteful, and unoptimized. A civilization thousands or millions of years older may consider such inefficiency crude. It may have passed through a noisy adolescence long ago and emerged into a phase where almost no detectable leakage remains. If many societies follow that path, then the search for obvious techno-signatures may be biased toward a brief transitional period that very few civilizations occupy for very long. The sky would then remain quiet not because technology is rare, but because mature technology is nearly invisible. There is also a moral version of concealment, less fearful and perhaps even stranger. An advanced civilization may choose not to interfere with younger ones, not from terror of detection, but from a principle of restraint. It may regard contact with emerging societies as disruptive, contaminating, or ethically irresponsible. The history of Earth provides countless smaller-scale warnings. Encounters between cultures separated by large differences in technology often end in domination, disease, distortion, and irreversible loss. A sufficiently reflective species may conclude that introducing itself to a developing civilization changes that civilization too deeply to justify the act. Under this view, silence is not defensive, it is protective. The hidden probe becomes not a sentry in fear of enemies, but an observer under strict rules. Watch, perhaps study, but do not intervene. The absence of contact then reflects a code rather than a crisis. This ethical version has a certain calm plausibility, yet it is not free of difficulties. It assumes not only intelligence, but discipline sustained over immense timescales. A civilization capable of crossing interstellar distances would likely contain factions, disagreements, eccentric individuals, and impulses not unlike curiosity, ambition, or carelessness. Can a whole species, or multiple species across the galaxy, maintain a perfect policy of non-interference forever? The problem resembles the challenge faced by any universal explanation of silence. It must account not only for the wisdom of many civilizations, but for their consistency. If even one group chooses to announce itself, interfere, colonize, or leave unmistakable artifacts, the silence breaks. The absence of such a break makes the required discipline feel extreme. Perhaps the discipline is not social but structural. A civilization that survives long enough to become truly advanced may do so precisely because it has transformed itself. It may no longer be a collection of competing biological individuals in the human sense. It may have merged into networked intelligence, machine substrates, or stable cultural forms in which reckless expansion loses appeal. It may value continuity over novelty, observation over conquest, and complexity of internal life over external display. Such a society might not regard the stars as territory to be occupied. It might see no reason to scatter visible markers across the galaxy. In that case, silence would not be a nervous strategy. It would be a consequence of maturity. The universe would contain intelligence, but intelligence would not behave the way younger species imagine. This line of thought introduces a deeper uncertainty about the human search itself. Much of the search for extraterrestrial intelligence is shaped by analogies to human behavior signaling, engineering, exploration, curiosity, expansion. But what if those are temporary traits rather than universal ones? What if civilizations initially resemble humanity just enough to become noticeable, then quickly transition into forms of existence that are quieter, denser, or more inward? A species may create immersive virtual realities so compelling that outward expansion loses importance. It may shift its center of activity into compact artificial habitats close to its star, optimized for efficiency and low visibility. It may explore by sending small machines rather than announcing its presence. It may discover that the richest frontier lies not in space but in computation, simulation, or inner worlds inaccessible to outside observation. The galaxy would then contain minds beyond counting, and still appear almost natural from a distance. Yet the concealment hypothesis has a cold edge that makes it difficult to romanticize. If silence is chosen because revealing oneself is dangerous, then humanity's own behavior begins to look suddenly exposed. Earth has not been quiet. Radio has leaked outward. Radar has swept space. Spacecraft have carried symbolic maps of human origin. Atmospheric chemistry now carries industrial signatures. Nuclear detonations have flashed above the planet. The emergence of a technological species on Earth is, in some respects, already visible to any nearby observer who happens to be watching carefully. If the galaxy contains hidden listeners, then humanity may already have announced itself without knowing the audience. This thought does not prove anything sinister. It only highlights an asymmetry. A young civilization can reveal itself accidentally long before it becomes capable of understanding the strategic implications. From here, the mystery becomes psychological in a way that remains grounded in observation. The question is no longer merely whether others exist, but what long survival does to a civilization's behavior. Human history offers examples of expansion and examples of secrecy, of contact sought eagerly and contact feared deeply. Which tendency scales upward into cosmic circumstances is impossible to know. The optimistic tradition imagines intelligence becoming wiser with age, gradually overcoming aggression, greed, and impulsiveness. Under that view, advanced civilizations remain hidden because wisdom teaches restraint. The darker tradition imagines intelligence learning fear, recognizing that the universe may contain predators, rivals, or incomprehensible dangers. Under that view, civilizations hide because wisdom teaches silence. Both stories produce the same sky. That is what makes the silence so difficult to interpret. A tranquil cosmos and a dangerous one can look identical from very far away. There is a further complication. Complete concealment may itself be a signal. If every mature civilization hides, then the visible galaxy becomes biased toward the young, the careless, or the doomed. The only societies likely to emit loud, wasteful, obvious signs are those in a brief phase before caution or destruction changes them. Humanity may be in exactly such a phase. That would mean the search for companions is also a search for civilizations balanced in a narrow interval of their development, old enough to use technology, young enough not to suppress every signature, and close enough in time that signals overlap. The resulting scarcity would be severe even if life were common. The great silence would then emerge not from universal loneliness, but from a filtering of visibility. Most minds would simply reside on the far side of detectability. This possibility is oddly compatible with another one. Hidden civilizations may still explore. They may still place probes in systems with young technological worlds. They may watch without speaking. The solar system, under such a scenario, could be studied in silence by entities committed to non-interference or strategic invisibility. Humanity would interpret the absence of open contact as evidence of absence, while in fact living under a form of distant observation too subtle to confirm. Again, this cannot be proven from current evidence, but it aligns with a sober technological expectation. Long-lived societies that value caution would likely separate observation from disclosure. The first presence would be silent. In the end, the concealment hypothesis does not solve the Fermi paradox so much as move it inward. The silence ceases to ask why no one is there and begins asking what intelligence becomes when it survives long enough. Does it grow quieter because wisdom deepens? Does it hide because danger is real? Does it refuse contact because contact harms? Or does it cease to care about visibility at all? Each version preserves the same dark sky. Each turns the lack of evidence into a clue about behavior rather than a clue about numbers, and each carries a different emotional temperature. One is protective, one is strategic, one is fearful, one is serene. Yet from Earth, all of them look like the same thing, a galaxy that reveals almost nothing. The stars continue to burn in public. Whatever intelligence may exist among them, if it exists, keeps to itself so well that the universe still feels undecided. The silence remains, not empty now, but disciplined, as though some immense conversation has chosen to proceed without sound. There is a gentler explanation for the silence, though it may be no less haunting. Civilizations may not hide, and they may not fail before reaching intelligence. They may simply miss one another in time. The galaxy is old beyond instinct, but any individual civilization may be brief. If that is so, then the Milky Way can contain many episodes of intelligence without ever allowing them to overlap. The paradox weakens not because life is rare, or because danger enforces silence, but because deep time is full of intervals wider than empires, species, and languages can endure. Seen that way, the question shifts from where are they to when were they. The answer may be that they were here too early or too late, their lights rising and fading in separate ages like short-lived blooms across a field. No single observer can ever see all at once. This idea gains force from the only case available. Human civilization, in anything like its present technological form, is astonishingly young. Agriculture appears only in the recent fraction of the species' history. Writing is younger still. Industrial power, electricity, radio, rocketry, digital computation, and the capacity to alter the whole planet belong to a span so narrow it is barely visible against geological time. The entire age of radio leakage from Earth covers little more than a century. Measured against the Milky Way's history, that is not even an instant. it is a flicker too small to deserve the word moment. If technological civilizations typically remain detectable for only a few centuries, or a few thousand years, then the chance that two arise close enough in both space and time to notice each other may be much lower than naive reasoning suggests. The galaxy could be dotted not with enduring neighbours, but with brief awakenings that almost never coincide. This is where Frank Drake's orchid image becomes quietly powerful. Some orchids flower for only a short time each year. The bloom is real, vivid, unmistakable to anyone present. Yet most of the time the plant appears ordinary or dormant. If civilizations are like that, then the galaxy may contain many of them across its history, each opening briefly into visibility before fading again. The problem is not that blooms never occur. The problem is that the observer arrives on the wrong day. A species living on one world may build radio telescopes while another, tens of thousands of light years away, has already passed through its technological bloom and vanished. A third may not arise for another 1,000,000 years. Their histories do not line up. No one hears anyone else because the intervals between civilizations are wider than the intervals within them. The more one considers the scale of time, the less fanciful this seems. On Earth, species appear and vanish, oceans open and close, continents collide and separate. Entire ecosystems dominate for tens of millions of years and then disappear into rock. Against such a backdrop, there is no obvious reason to assume that intelligence, once it appears, must remain stable forever. Civilizations are not simple organisms. They are layered systems dependent on energy, climate, social continuity, infrastructure, and increasingly fragile webs of technology. A prolonged war, ecological collapse, engineered pathogen, loss of critical resources, or disruption of global networks could set them back severely. Even without total extinction, a civilization may fall below the threshold of detectability. Radio silence can follow not from death, but from regression. Knowledge can be lost, habitats can fragment, industrial systems can contract. A world that once sent signals into space may return to a quieter state for centuries or millennia. From afar, it would look as though intelligence had vanished. There is a temptation to imagine progress as irreversible. Modern history encourages this illusion because, over a few recent centuries, technology seems to accumulate and accelerate. But deep time warns against straight lines. Civilizations on Earth rise, expand, fracture, and disappear even on much smaller scales. Their monuments erode, their languages vanish, their records burn. The global industrial order is far more powerful than any previous one, but it is also more entangled and more vulnerable to systemic failure. Electricity, digital communication, satellite navigation, semiconductor manufacturing, long supply chains, and coordinated institutions create extraordinary capability, yet they also create points of fragility. A civilization able to build space telescopes may still prove unable to remain coherent for 10,000 years. The question becomes unsettling when stretched further. Can any technological species remain stable for 100,000 years? 1 million, 10 million. The galaxy does not ask whether intelligence can emerge, it asks whether intelligence can persist. This leads naturally toward ruins. If civilizations bloom briefly and then die, perhaps the Milky Way is not empty at all. Perhaps it is archaeological. The evidence of past intelligence may exist not as active signals but as fossils, artifacts, abandoned machinery, altered planets, or strange isotopic fingerprints left on worlds whose builders are long gone. This vision is both comforting and disturbing. It suggests company, but only in the form of aftermath. The galaxy becomes a place where intelligence has appeared, perhaps many times, only to leave behind traces too scattered, too ancient, or too subtle for current detection. Humanity then inhabits not a lonely present, but a late chapter in a long-forgotten history. Yet if ruins exist, why have none been found? One answer is the scale and incompleteness of the search. Humanity has barely begun to inspect the solar system in detail, let alone the wider galaxy. Ruins on distant exoplanets would be extraordinarily hard to identify with present instruments unless they altered the planet on a massive scale. Even local artifacts may remain hidden for immense spans. A dead probe on an asteroid, a buried structure on Mars, a cluster of inert machines in the outer solar system. All could escape notice easily. Time itself also conspires against preservation. Atmospheres erode exposed structures, tectonics recycles crust, impact pulverize surfaces, stars evolve. Some planetary environments are good archives, others ruthless erasers. Earth is a poor keeper of very ancient surface history, because its active geology destroys and remakes the crust. The Moon is better. Mars may preserve some ancient surfaces. Small airless bodies may preserve still more. But the number of places to inspect is enormous, and the expectation of finding alien ruins remains so low that few searches are optimized for it. The deeper difficulty is not only finding ruins, but recognizing them. What does a dead civilization look like after 1 million years? 10 million? 100 million? Most human ideas of archaeology rely on continuity of scale and material. Stone walls remain walls, metal tools remain tools, but across geological spans, artificial materials corrode, fragment, get buried, or are transformed by radiation and impact. A vast orbital infrastructure may decay into unremarkable debris. A planetary industry may leave subtle chemical scars rather than visible monuments. Even Earth's own industrial age, projected far into the future, may leave a complex but ambiguous layer in the rocks rather than obvious cities. Some researchers have even asked whether a prior industrial civilization on Earth, tens of millions of years in the past, could leave traces recognizable after such spans. The answer is that some signals might survive, but not in easy forms. If that is true here, it is even more true elsewhere. The galaxy may contain remnants that do not announce themselves as remnants. There is also the possibility that civilizations die in ways that erase their records almost completely. A world devastated by war, runaway climate, asteroid impact, or stellar change may lose not only its species, but the preservation conditions needed to retain evidence. Oceans can swallow coastlines where industry once concentrated. Glaciation can grind landscapes flat. Volcanism can blanket continents. Atmospheres can oxidize or strip away exposed materials. A planet rich with history can become outwardly silent again. From the standpoint of distant observation, a dead technological world may differ little from a natural one unless the right instruments look at the right chemistry at the right moment. And still, the timing problem remains even without total destruction. Civilizations may persist in forms that are quiet, local, or no longer interested in external signaling. A species might achieve a stable equilibrium with low energy use. It might retreat into virtual or subterranean environments after environmental crisis. It might abandon expansion for reasons cultural or practical. In such cases, the period of high detectability may be very short, even if the civilization continues in some reduced or transformed form for much longer. Humanity itself may currently occupy an unusually loud phase: industrialization, fossil fuel burning, artificial illumination, radio leakage, and growing planetary engineering make Earth conspicuous in ways that may not last. Future technology could become cleaner, more efficient, and harder to see. If so, Even surviving civilizations would leave only brief visible windows in cosmic time. The orchid analogy then becomes more than a metaphor. It becomes a structural feature of detectability. A civilization may spend most of its existence either unborn, pre-technological, post-industrial, hidden, or gone. Only for a relatively narrow interval does it bloom into visibility. If these intervals are short and widely separated, the galaxy remains apparently silent even if intelligence is not especially rare. The silence arises from poor synchronization. This answer is strangely elegant because it turns abundance against itself. The more time available in the galaxy, the easier it becomes for civilizations to be scattered across that time without meeting. Deep time does not guarantee overlap. It may ensure non-overlap. Yet the elegance is unsettling because it refuses comfort. A galaxy of brief blooms offers no assurance that humanity will escape the same pattern. On the contrary, it raises the possibility that every civilization reaches a point where its detectability collapses. Some collapse because they die, some because they mature into quiet, some because they lose interest in broadcasting, some because they transform beyond easy recognition, whatever the reason. The visible phase remains short. The stars then become not a community of neighbours, but a graveyard of missed appointments. Somewhere, perhaps, worlds have already known mathematics, music, astronomy, memory, machines, and loss. Somewhere, atmospheres may carry the faint residues of vanished industries. Somewhere, on cold moons or barren planets, the husks of instruments may still face the stars, their makers erased by ages no one now recalls. But the sky at present remains dark because present is too narrow a category for cosmic history. This possibility also changes the meaning of exploration. If the galaxy's other civilizations lie mostly in the past or future, then direct contact may be rare or impossible, but evidence of intelligence could still wait in matter rather than signal. The search for extraterrestrial life becomes partly a search for extraterrestrial archaeology. A strange mineral distribution, an anomalous isotope ratio, a geometric arrangement on a dead world, a fragment of alloy where no natural process should place it. These might someday carry more significance than any radio pulse. The universe may not speak in real time, it may preserve whispers in stone. Humanity has not yet searched widely enough or sensitively enough to know. In this view, the Great Silence is not a verdict against life. It is a statement about timing, impermanence, and the difficulty of overlap. Civilizations may rise more often than feared, yet still leave the present era feeling lonely, because they're separated not only by light years, but by epochs. The sky then becomes layered with unseen histories. Every star may host not just worlds, but possible intervals of awakening, each with its own narrow bloom. Some may be ahead, some may be behind, some may never come. Humanity sits in its own brief flowering, listening outward from a single season and hearing nothing back. That may not mean the garden is empty. It may mean the blossoms open and fall under different suns, at different ages, too early or too late for any two to share the same night. The most unsettling version of the Great Filter does not lie behind humanity in the buried strangeness of biology or the rare calm of planetary history. It lies ahead. In this version, civilizations do arise. They survive the long climb from chemistry to cells, from cells to complex organisms, from complex organisms to minds, and from minds to machines. They reach industry. They harness energy on a planetary scale. They build weapons, networks, laboratories, and engines. They begin to step away from the surface that made them. From a distance, they would look like success stories. Yet something waits just beyond that threshold. some recurring difficulty woven into the nature of technological intelligence itself. It does not prevent life from appearing. It does not prevent thought, language, agriculture, metallurgy, or science. It intervenes later, in the dangerous interval when a civilization becomes powerful enough to alter its planet, powerful enough to destroy itself, and not yet wise enough, unified enough, or stable enough to manage that power for the spans required to reach the stars in any lasting way. This possibility carries a special force because it does not depend on unknown biology or exotic astronomy. It draws much of its power from familiar history. Human civilization has already crossed several thresholds that would have seemed godlike to earlier ages. It can split the atom, edit genes, alter the chemistry of the atmosphere, simulate minds in machines, and launch instruments beyond the solar system. It can see galaxies whose light began its journey before Earth existed in any recognizable form. It can also poison, burn, destabilize, and weaponize on scales no previous species has ever approached. This same intelligence that reveals nature also amplifies risk. This is the central unease of the future filter. Knowledge and danger do not grow separately. They grow together. Every new domain of mastery expands the range of both creation and failure. A civilization may therefore become most vulnerable not when it is primitive, but when it is advanced enough to magnify its own mistakes. The nuclear age offers the clearest early example. Once a species learns how matter binds and breaks at its deepest levels, it gains access to energies capable of ending cities in moments and damaging civilization in an afternoon. On Earth, this knowledge arrives within a very short time of industrial maturity. The interval between the first powered flight and the first atomic weapons is tiny on historical scales. A species barely learning to leave its atmosphere suddenly acquires the means to devastate its own world. This compression matters. It suggests that intelligence may repeatedly discover destructive power before it develops reliable political mechanisms to contain it. Earth's history provides several moments when catastrophe comes frighteningly close. Miscalculation, error, warning systems, military tension, and the logic of deterrence combine to produce situations in which large-scale destruction is avoided not by certainty, but by restraint, chance, or the decisions of a few individuals under pressure. The fact that civilization survives these moments does not remove the danger. It reveals how narrow the margins may be. A future filter need not take the form of immediate extinction. It may work more subtly. A planetary war might not erase a species completely, but could break the continuity of technological progress for centuries or longer. A chain of infrastructure collapse, famine, disease, and political fragmentation could push a civilization downward below the threshold required for sustained scientific or spacefaring expansion. The stars do not care whether a species vanishes outright or merely loses its capacity to reach them. From the perspective of the Fermi paradox, either outcome is enough. The galaxy remains silent if civilizations repeatedly destroy the conditions for long-term outward growth. Climate change adds another layer to the pattern because it emerges not from deliberate hostility, but from ordinary success. A civilization learns to use stored energy, multiplies production, transforms landscapes, fills the atmosphere with byproducts, and then discovers that the very engine of its growth alters the planetary system on which all future growth depends. This is a different kind of trap. It is slow enough to deny urgency, global enough to resist simple solutions, and cumulative enough that delay compounds the cost. It reveals a weakness in intelligent species that may be more general than any particular technology. Coordination on planetary scales is hard. The tools needed to change a world may arrive long before the social structures needed to manage that change collectively. A civilization may therefore be clever enough to engineer a crisis and too divided to prevent it. If this pattern is common, then many worlds may host species that industrialize, destabilize their climates, fragment politically, and spend the critical centuries of their technological adolescence trapped in self-created turbulence. Biological risk introduces another kind of threshold. Once a civilization understands enough genetics, microbiology, and medicine to heal, extend life, and prevent disease, it also acquires the possibility of designing pathogens, accidentally or deliberately, with consequences that escape any local scale. Natural pandemics already test social resilience. Engineered ones could be more selective, more contagious, or harder to contain. Here again, the problem is not merely invention but distribution of capability. Knowledge spreads, tools become cheaper, barriers to entry fall. A civilization does not need universal malice for danger to rise. It needs only enough competence in enough hands, combined with error, extremism, secrecy, or indifference. The broader lesson is chillingly simple. As technical power becomes more widely available, the number of failure points multiplies. The species as a whole may be intelligent, but survival begins to depend on the restraint and judgment of innumerable actors across generations. Artificial intelligence deepens the same pattern while adding a more profound uncertainty. A civilization may eventually create systems that outperform biological minds in planning, design, surveillance, optimization, or war. It may do so gradually, integrating machine reasoning into every institution, or rapidly, in bursts of competition. The danger is not only the familiar fantasy of rebellion, it is the possibility that a species builds systems too consequential to regulate and too entangled to abandon. Decision-making may become faster than deliberation. Economies may reward deployment before understanding. Military incentives may drive escalation. Political actors may seek advantage through systems whose behavior they do not fully control. Even if no dramatic rupture occurs, a civilization may hand over critical functions to processes whose goals, biases, and interactions amplify instability. The result could be authoritarian lock-in, cascading accidents, ecological mismanagement, autonomous conflict, or subtler forms of social erosion that hollow out the institutions needed for long-term survival. In that case, the filter is not an explosion, but a drift into conditions from which coherent civilization no longer recovers. What makes the future filter so persuasive is that it does not require any one threat to be universally fatal. It can arise from accumulation. Nuclear weapons alone may not end every civilization. Climate disruption alone may not either. Engineered biology, uncontrolled machine systems, ecological collapse, resource wars, or informational fragmentation may each be survivable in isolation. But a technological species may face many of them at once, layered across the same historical interval. This creates a convergence zone. For perhaps a few centuries or a few millennia, a civilization becomes capable of modifying every major system on which it depends, while still remaining emotionally, politically, and institutionally shaped by much older instincts. Competition, short-term advantage, tribal identity, prestige, denial, and fear remain active while the tools available to those instincts become planetary. The mismatch may be the true filter. Intelligence outgrows its ancestral operating system faster than it outgrows its technologies. Seen this way, the silence of the Milky Way begins to resemble not emptiness but repeated interruption. On many worlds, perhaps, life climbs all the way to science. Telescopes are built, the stars are named, equations are written, energy use rises, machines spread. Then something happens in the narrow window between first industry and interstellar durability. Perhaps there is war. Perhaps there is ecological overshoot. Perhaps there is engineered disease, machine misalignment, social collapse, or a more mundane failure of coordination that slowly closes the future. The specifics may differ. The structure remains. Civilizations become too powerful for their maturity. They reach the gate of outward expansion, carrying internal instabilities large enough to stop them. The galaxy then fills not with empires but with aborted trajectories, each world brilliant for a moment, then quiet again. This version of the Great Filter is especially unnerving because the laws of nature do not rescue anyone from it. Nothing in physics forbids interstellar travel in principle. Nothing obvious prevents a sufficiently patient species from becoming multiplanetary, then spreading more widely. The obstacles are not cosmic but civilizational. They emerge from how intelligence behaves when it gains leverage over matter, faster than it gains leverage over itself. That is a more intimate danger. A rare planet explanation leaves humanity fortunate. A hidden civilization explanation leaves humanity ignorant. A future filter leaves humanity implicated in the pattern it is trying to explain. Even here, however, certainty is impossible. Human history is too short to prove that technological societies cannot stabilize. One can imagine another outcome. As power grows, institutions may adapt. Catastrophic weapons may be constrained. Energy systems may become cleaner. Global coordination may strengthen under pressure. Artificial intelligence may be aligned and governed. Biological tools may be regulated successfully. Civilization may pass through its dangerous adolescence and emerge into a longer era of maturity. In that case, the future filter would not apply, or would at least be less severe than feared. The silence would need another cause. But the concern persists because the passage through adolescence appears narrow and crowded with hazards. While the evidence of other survivors remains absent, a species cannot infer doom from that absence alone. Yet it also cannot easily ignore the possibility that many others fail at the same stage. There is an even colder angle to the argument. A civilization may not need to annihilate itself to disappear from the galactic record. It may simply fail to become multiplanetary before some external clock runs out. Planets are finite, stars evolve, impacts remain possible, climate systems shift, geological engines cool. If a species remains confined to one vulnerable world for too long, then even modest setbacks may prove decisive over deep time. The future filter could therefore be defined not as destruction, but as the inability to escape local fragility before fragility catches up. In this sense, becoming multiplanetary is not a romantic ambition, but a statistical strategy against extinction. A civilization that never expands beyond one world keeps all of its meaning. Memory and intelligence in a single basket exposed to one chain of contingencies. Enough time guarantees bad luck eventually. The galaxy may be silent because most civilizations never buy themselves enough redundancy. This possibility reframes the entire Fermi paradox as a question about timelines. How long does a species have between the moment it can destroy itself and the moment it can reliably spread beyond its homeworld? If the first arrives much earlier than the second, then the filter is severe. A society must navigate centuries or millennia of intense risk before acquiring the resilience that interplanetary existence might bring. For humanity, that interval has already begun. Nuclear danger arrives. Climate danger arrives. Machine danger begins to emerge. Biotechnology accelerates. Yet truly self-sustaining settlements beyond Earth remain unrealized. The species stands in a narrow corridor between newfound power and unfinished escape. That does not mean failure is inevitable. It means the structure of the problem matches the logic of the Great Filter too well to dismiss lightly. In the end, the future filter remains a hypothesis, but it is a hypothesis with a grim elegance. It explains the silence without asking life to be rare and without requiring all civilizations to hide. It says simply that many worlds produce intelligence, and intelligence often becomes hazardous to itself before it becomes secure among the stars. The tragedy, if tragedy is the right word, is not that the universe refuses to generate minds. It may generate them often enough. The tragedy is that minds may repeatedly awaken into powers their social evolution has not prepared them to bear. They look outward, build the first instruments of escape, and then are stopped by the turbulence within. If this is true, then the Milky Way may not be quiet because no one ever rises. It may be quiet because almost no one stays risen long enough. Somewhere in that possibility lies one of the darkest readings of the Great Silence. The missing civilizations are not missing in the distant past or in inaccessible galaxies. They are missing from the future they almost reached. If the Great Filter does not wait in the future, then it may already stand far behind, buried so deeply in the history of life that most worlds never come close to crossing it. This is the other severe possibility, and in some ways it is even stranger than self-destruction. It suggests that the galaxy is quiet not because civilizations rise and fall, nor because they hide, nor because they miss one another in time, but because almost none ever begin the long climb toward intelligence at all. Not in the sense of simple life. Simple life may be common. It may arise wherever chemistry finds enough persistence, water, energy, and time. Oceans beneath ice, warm ponds on young planets, mineral pores around hydrothermal vents, thin films of moisture in ancient rock, all may host the first fragile experiments of biology. The severe possibility concerns what happens next. On Earth, the first step may arrive comparatively early. The later steps, the ones that matter for complexity, may be so improbable that a whole galaxy can remain full of microbes and still produce almost no civilizations. In that version of the story, the silence is not a warning about what intelligence does to itself. It is evidence that intelligence almost never appears. Earth's own timeline is the reason this thought carries weight. Life seems present very early in the planet's history, at a time when Earth is still geologically young. That fact is often taken as encouraging. It implies that the origin of life may not require miraculous rarity. Given the right conditions, chemistry may move toward metabolism and replication with a certain natural insistence. But when the later history of Earth is examined, optimism begins to thin. For the better part of 3 billion years, nothing more complex than single-celled life dominates the planet. That is not a short delay waiting to be filled. It is most of the story. If a world were observed from afar during those ages, it might have oceans, an atmosphere altered by biology, and a rich microbial biosphere. Yet it would contain nothing resembling forests, animals, nervous systems, or tools. It would be alive and still, in terms relevant to the Fermi paradox, almost infinitely far from civilization. This long interval raises a terrible possibility. Maybe the origin of life is easy enough, but the origin of complex life is the true abyss. At the center of that abyss stands the eukaryotic cell. Modern biology points again and again toward the importance of this transition. The cells that build animals, plants, and fungi are not merely more elaborate versions of simpler cells. They are structured around an internal complexity that may depend on an ancient merger, a symbiotic event in which one organism becomes incorporated into another and remains there, transformed into a power source. Mitochondria, the tiny engines inside complex cells, seem to descend from such a partnership. Without them, large genomes, internal compartmentalization, and the energy demands of multicellular bodies may be difficult or impossible to sustain. What makes this event so striking is not only its importance, but its apparent singularity. On Earth, as far as current evidence can tell, this deep cellular architecture evolves once. Every complex creature on the planet inherits the consequence of that one ancient convergence. If this reading is correct, then one of the decisive thresholds in the history of intelligence may depend on a bizarre and rare biological encounter that does not happen automatically and may not happen twice on a given world, even if life flourishes there for billions of years. This is why the deep past filter feels less dramatic and more absolute. A civilization can survive wars. It can learn from climate crisis. It can build safeguards against dangerous technologies. But a planet cannot negotiate its way around an evolutionary step that never occurs. If complex cells fail to arise, then no amount of future time helps. The biosphere may diversify endlessly at microbial scale. It may fill every niche available to simple organisms. It may alter atmospheric chemistry, build mats, reefs, and colonies, perhaps even evolve exquisite forms of single-celled cooperation. Yet without the right breakthrough, it may never pass into the domain of bodies large enough, intricate enough, and energetically powerful enough to support brains, hands, language, or machinery. A world can remain busy and biologically rich forever, while never producing anything that sends a signal into the dark. Even once complex cells appear, nothing guarantees rapid progress. Multicellularity itself seems to arise more than once on Earth, but not every multicellular lineage becomes anatomically ambitious. Many remain simple. The rise of animals requires further innovation, cell specialization, developmental control, long-range signaling, mobility, predation, sensory systems. Then nervous systems become elaborate. Then some creatures begin to model their environment, remember, cooperate, and solve problems. Intelligence appears in many degrees across Earth's living world, but technological intelligence in the full sense seems to require still more unlikely convergences. A lineage must not only think, it must manipulate. It must persist through ecological upheaval. It must benefit from social learning. It must accumulate information across generations. It must inhabit an environment where tools matter. Fire can be controlled, materials can be worked, and memory can become culture. At every stage, there are branching paths that lead to flourishing forms of life with no prospect of astronomy. Earth itself demonstrates this. Dinosaurs dominate for immense spans and never build observatories. Marine mammals become highly intelligent and remain trapped, as it were, by the physical limits of their environment. Octopuses solve problems and vanish into short lives. Intelligence in a general sense may not be vanishingly rare. Intelligence that turns into cumulative technology may be. This deepens the sense that the great filter behind humanity may not be one gate but a narrowing corridor. Life begins. Then almost everywhere it stays simple. On a few worlds, perhaps complex cells emerge. On fewer still, multicellularity becomes ecologically dominant. On fewer still, nervous systems reach high sophistication. On fewer still, one species among many acquires the exact mixture of embodiment, environment, memory, sociality, and luck required for cumulative technology. By the time the first radio transmitter appears, the original abundance of habitable planets may already have been reduced by a sequence of improbable biological lotteries. The galaxy could therefore contain countless living worlds and still average less than one technological civilization at any given time. In such a cosmos, the paradox softens without becoming less mysterious. The silence no longer reflects failure of search. It reflects the rarity of the target. This possibility has an odd relation to the places in the solar system that now attract scientific interest: Mars, Europa, Enceladus, Titan, perhaps even deeper and stranger worlds in the outer darkness. All suggest that environments suitable for basic life may not be exceptional. Mars once has rivers and lakes. Europa likely maintains a deep ocean beneath ice. Enceladus vents water, salts, and organic compounds into space. Titan runs a chemistry unlike Earth's, but no less intriguing for that difference. If even one of these places is found to host microbial life, the discovery would be revolutionary. Yet it would not, by itself, weaken the deep past filter. It might strengthen it. A universe where microbes are common but civilizations absent is exactly what this version predicts. The more often life begins in simple form, the more pressing becomes the question of why so little of it seems to progress toward complexity, visible across the stars. There is an even more sobering extension. The age of the universe itself may matter. Earth takes almost 4 billion years to produce a technological species, and that span occurs under unusually persistent conditions. Suppose, then, that Earth is not slow. Suppose it is fast. Suppose many living worlds need much longer for the full sequence. Perhaps because key transitions are rarer, because planetary stability is harder to maintain, or because evolution usually wanders through unproductive spaces for immense periods before finding its few transformative breakthroughs. Then the problem becomes sharper still. The universe may simply not be old enough, in most cases, for cell to civilization. A typical world may begin life, remain microbial for ages, perhaps produce complexity late, perhaps never, or reach intelligence only when its star is already shifting out of the phase that makes long surface habitability possible. In this view, humanity does not live in a galaxy that failed to produce many peers. It lives in a galaxy still waiting for most of its possibilities to mature. The silence would then be temporary in a cosmic sense, but total in the present. This idea has a lonely elegance because it turns humanity into an early event rather than a central one. Earth might sit on the fortunate edge of evolutionary timing, not because its outcome is supernatural, but because it happens to occur sooner than average on a planet stable enough to support it. That would mean the current Milky Way could indeed contain only one civilization, with many more potential ones stalled in their microbial or pre-technological ages. The night sky would then be full of worlds rich in future possibility and empty of present conversation. Some of those worlds may eventually produce forests, then animals, then minds, but not yet. Not in time to answer. The great silence would be real, but not eternal. It would be the silence of a universe in which most stories have begun, but few have progressed far enough to speak. There is a harder version still. Perhaps even complex multicellular life is more a fluke than a stage. Perhaps Earth's biosphere is not merely early, but extremely unusual. The so-called fateful encounter that gives rise to complex cells happens once here. Snowball episodes, oxygenation, mass extinctions, continental arrangements, climate buffers, and evolutionary contingencies then align over immense spans. The result is not inevitable intelligence, but a long sequence of low-probability recoveries. If this reading is close to truth, then phrases such as habitable planet and Earth-like world become deeply misleading. A planet may resemble Earth in size, orbit, and temperature, and still remain forever outside the true corridor that leads to complexity. From a telescope's perspective, it would look promising. From biology's perspective, it would be a cul-de-sac. A galaxy filled with such worlds would appear rich in possibility while remaining effectively empty of minds. This is one reason the Fermi paradox can become more intense rather than less as astronomy advances. Every new exoplanet discovered in a temperate orbit encourages imagination. but biology whispers that the crucial thresholds may be invisible. A world does not need the right distance from its star. It needs the right 4 billion years. It needs the right cellular breakthrough. It needs the right atmosphere at the right time, the right extinctions, the right recoveries, the right developmental inventions, the right ecological pressures. It needs, perhaps, the right kind of accident repeated just rarely enough to look like destiny in hindsight. No telescope can yet see that chain directly. So the galaxy may appear full of second Earths, while containing almost none in the only sense that matters for the paradox. If this is the true position, then humanity occupies an unusual responsibility, though not in any grandiose or moralizing way. The point is simpler and colder. If technological intelligence is genuinely rare, then the loss of one civilization is not balanced by abundance elsewhere. Meaning, memory, mathematics, music, history, science, art, all the strange internal weather of conscious life may not be widely duplicated across nearby space. Earth would then be not one inhabited island among many, but a rare concentration of complexity in a sea of otherwise speechless worlds. A destroyed civilization would not merely silence one planet, it would erase one of the few places where the universe has become capable of noticing itself in this region of the galaxy. This thought is severe, but it emerges directly from the biology-driven reading of the filter. When civilizations are rare enough, each one becomes statistically important. Yet even here, certainty remains out of reach. Biology on Earth is one example, and one example can mislead. Perhaps complex cells arise often through routes not yet imagined. Perhaps other chemistries produce complexity without anything like mitochondria. Perhaps intelligence on other worlds emerges from oceanic life, aerial life, fungal networks, or substrates so different from Earth's that current categories conceal more than they reveal. The fact that one path on Earth appears narrow does not prove all paths are. It only proves that the one known route is long, contingent, and difficult enough to raise suspicion. The universe may still contain surprises large enough to overturn every gloomy inference. A single discovery of independent complex life within the solar system would radically alter the argument. A confirmed biosignature from an exoplanet would change it again. An unmistakable technosignature would transform it completely. Science remains open precisely because it does not close around even its most persuasive suspicions. Still, until such a sign arrives, the deep past filter retains its stark power. It explains the silence with almost brutal economy. The galaxy is not full of missing empires, hidden fleets, or vanished ruins. It is full of worlds where life either never begins or begins and remains simple. It is full of oceans with microbes, rocks with dormant spores, atmospheres shaped by tiny metabolisms, and perhaps countless biological experiments that never cross the threshold into visible complexity. The stars can number in the hundreds of billions. The planets can number in the trillions. None of that guarantees minds. Quantity does not rescue a process if the process narrows through enough improbable steps. The great silence then ceases to be paradoxical in the dramatic sense. It becomes the expected sound of a galaxy where biology rarely climbs all the way from cell to civilization, and yet the strangeness remains. Because if that is true, then Earth itself becomes one of the rarest known outcomes in the natural world, a place where for almost 4 billion years the thread does not break. The improbable transition occurs, multicellular bodies proliferate, intelligence finds hands and fire, memory becomes writing, and matter learns to wonder whether it is alone. That does not end the mystery. It makes the mystery more intimate. The stars stay quiet. The question turns inward. Was the great obstacle already crossed long ago? Hidden in the dark age of single cells, while no one was there to see it happen. Did the hardest step occur so far in the past that modern civilization mistakes itself for the beginning, when in fact it is the late and fragile consequence of one ancient biological accident? The silence offers no confirmation. It only leaves open the possibility that the rarest event in the galaxy is not interstellar travel, not advanced engineering, not cosmic empire, but the first world where life refuses to remain small. Across all these possibilities, the silence remains larger than any single answer. It may come from distance, from concealment, from extinction, from timing, from biology, or from some combination still hidden beneath the limits of present knowledge. A galaxy with hundreds of billions of stars should feel crowded with futures, and yet it presents itself as a place where intelligence, if it exists beyond Earth, leaves almost no clear trace. That is what makes the Great Filter so difficult to set aside. It is not merely a theory about aliens. It is a way of looking at the night sky and recognizing that every star may hold a story that never reaches the stage of signal, or reaches it only briefly, or passes through it in silence. Perhaps the Milky Way is full of beginnings that never become civilizations. Perhaps it is full of civilizations that do not last. Perhaps it is full of watchers who have chosen never to speak. Or perhaps the true answer is stranger than any of these, waiting in data not yet gathered, on worlds not yet seen clearly, in atmospheres not yet read, or in ruins not yet recognized for what they are. Earth then hangs in a peculiar light. It is either one example among many not yet found, or one of very few places where matter has crossed the long bridge from chemistry to consciousness. That uncertainty is what gives the question its strange power. The sky does not merely look empty, it looks unfinished, as if the universe has revealed enough to sharpen the mystery and then withdrawn just before the final clue. Somewhere beyond the reach of present certainty, life may be stirring under ice, drifting in hidden seas, or thinking beneath unfamiliar skies. Somewhere else, perhaps, intelligence has already risen and fallen, leaving only cold worlds and buried traces. And here, on one small planet circling one ordinary star, the question remains suspended in the dark, patient and unanswered, as the stars continue to shine with the same calm indifference they have always shown, and the silence keeps its secret for one more night.